couple spaces to fill in there. We're doing vectors. The main thing about a vector is it has a magnitude and a direction. If you just have a magnitude, it is called a scalar. And distance and speed are both scalars unless you give them a direction. If I go 3 kilometers, you're like, you don't know where I went. I could go 3 kilometers in any direction. But if I told you I went 3 kilometers north, then that could be a vector. So distance is a scalar, but displacement is a vector because it has direction. So sometimes early on through school, you're kind of like, well, why do sometimes we say velocity and sometimes we say speed? Aren't they the same thing? And later you learn that velocity has a direction. And speed is just how fast you're going, but you're not saying which direction you're going. So your car tells you the speed, but then you would have to say, oh, I'm going 80 kilometers per hour east. So what I'd like you to do is read the following and either put an S for scalar, V for vector, or if you think it's neither, put an N. All right, let's check how you did. Outside temperature is 15 degrees. Oops, I haven't unscrewed. That is a scalar.
Oh, hell of a scalar.
Traveling, that's just a speed. You have no direction, so that's just a scalar. This one gives you the direction of north and the speed, so it has a direction and a magnitude. Wind is blowing from the south is neither, because you don't have an amount, you just have a direction. So direction only. Upwards vertical force, that's a vector. Mass of 5 kilograms is just a scalar. Car is speeding eastward is neither. This is a vector. And the last one is a vector because the direction is down. So we draw vectors by doing a straight line and an arrowhead. Sometimes that arrow, like in this diagram, sometimes you'll see the arrow in the middle. I often put the arrowhead right on the end because it kind of feels. Sometimes I put it in the middle because sometimes you put an arrowhead on the end, sort of makes you think, oh, does it just keep on going like a line? So that might be the reason sometimes the arrow's in the middle, but if you're dealing with vectors and put the arrowhead on the end, that is fine as well. Now we have something called a position vector. A position vector always starts at the origin and goes to some point, x, y. And so we write our vectors kind of like matrices. We write them as a column. Column vector is kind of like a 2-by-1 matrix. And you're going to find that a lot of the math that we do has similar things in matrices and vectors as well. Now, some textbooks will show vectors by bolding them. The problem with bolding things is when you're writing notes, it's very hard to do. So what we'll often do is we'll draw an arrow over top of the vector. And you will see that sometimes people make a full arrowhead, sometimes they underline it, sometimes in notes it's bolded, and me personally, I don't know if I got lazy in university, but I would always draw my vectors with a half arrowhead, because you could do it without having to lift your pen. So yeah, that's how you'll often see me do it. Sort of like an arrowhead, but I just didn't draw the other half. So there's some notations for vectors. So we use a little letter for the vector with a we're gonna put the arrows over top as much as possible, so you'll see that the most. You can also write the endpoints, like it goes from O to P, and put an arrow over top of that as well.
This is like,
Oh.
no, but it's like not, it's not like about that.
Okay.
Are those Prince pants?
They are Prince pants.
That's so funny.
What was more funny was the Prince shorts yesterday.
Oh my god.
But I had, that was, they were way too short. There's no way. I was a good sport. This is better. You're welcome. I was a good sport. I would have been in the office for dress code violation. Oh, okay, I put it on mute. All right, good. It was recorded in silence. Now we're back on. In the diagram below, the line OA represents the vector A. So here in your notes, you can imagine drawing a little arrow over that. It's bolded, right? We can also write it as the column vector 6, 3. No, we're gonna put an arrow here. In the IB course, where vectors used to be a part of that course, students had to underline them. That was the only notation that was accepted. And I don't like the underline part. I like the little arrowhead over top. Much better. So we're going to do the arrowhead over top. Even though this is allowed, we're going to do that because it's easier and nicer. There it is. Or you can have the full arrowhead if that bothers you, the half arrowhead. So in a column vector, the x represents the x. Well, the top one is however you move things horizontally, and the bottom one is whatever is moved in the vertical direction. So consider 2 points, A and B. A is at 1, 2, and B is at 3, 6, and it's shown in the diagram there. If you wanted to go from A to B, we would move 2 in the positive direction, sorry, this arrow, we're going from A to B, the arrow would be that way. 2 in the positive direction and 4 units up. So you could represent this, A to B, as the column vector 2, 4. And B to A, well, now I would have to be going back 2 and down 4, then its column vector would be negative 2, negative 4. A unit vector is a vector that has a length of 1. So the standard unit vectors, and we'll write them with arrowheads over top, are I, 1 to the right, and J, 1 up. So 1 to the right is drawn there in green, 1 up, drawn in blue. And we can always write any column vector in its unit vectors. So 2, 4 is the same as 2I plus 4j, and we can have those arrowheads over top of I and j. If you draw or write a vector and forget the arrowhead, that's a notation sort of like forgetting units, like a half mark off. It's kind of like forgetting the plus c in integration. So we can always write things in the unit vector form. So to get to 2, 4, we could go 2I with an arrow over top, plus 2j with an arrow over top, 4j, sorry. So what I'd like you to do on this next one is for each of these, here's the answer for the first one, for vector A. I'm adding all the arrowheads over top. Vector A would be 3I plus 2j, or as a column vector, it would be 3, 2. I would like you to write the unit vector form and the column vectors for B, C, and D. And see if you counted right. I'll add the arrowheads. Sometimes I find the arrowheads over the I and J annoying because there's a dot. Like over an A, you're like, no problem. But with the dot, it's sort of like, ooh. Anyway.
That's true. Can we capitalize capital J?
No, that's all lowercase. Yes.
You see Breaking Bad?
Yes. Lots of not.
Bryn's never seen Breaking Bad.
She should.
I was saying she should say she's dressed like Walter White.
There you go. Now, the main reason you're going to fall in love with vectors is they make math in 3 dimensions way better than our regular math. But you learn regular math like geometry, equations of lines. You learn that in 2 dimensions in high school because for the most part you're writing your notes on a piece of paper. And no one has bought 3-dimensional paper yet, where you write in 3-dimensional space and have your notes that way. That would be very confusing. So we do all of our math in 2 dimensions, and so that's how we've been graphing and drawing parabolas and cubic functions and all sorts of things. But real life, lots of real life is in 3 dimensions. I don't know if you've noticed. So vectors are going to be really good in 3 dimensions. So most of our math is going to be using the unit vectors I, J, and also K, where K is along the z-axis, which moves up and down. So if you had -9, 3, and 4 as a column vector, what you would draw is you would go along your x-axis. First of all, I'm going to highlight in light blue here. This is your x and y axis. Those are still 90-degree angles, but you imagine having that as a piece of paper in 3 dimensions on a table, it would look like that. Then you draw your z-axis, which I'll do in green here, up and down from that. So when drawing a point like -9, I would go 1, 2, 3, 4, 5, 6, 7, 8, 9. And I would go 1, 2, 3. And I'd find this point right here would be -9, 3 in 2 dimensions. Then going up 4, 1, 2, 3, 4, I'm going to draw right from my origin. Going up 4 is that length. So I would have to go that length up again from my point -9, 3 to get my final point to be able to draw on a two-dimensional piece of paper a three-dimensional vector. I would like to have like a three-dimensional laser beam space here where I could like just draw things in 3 dimensions. And you'd have little three-dimensional spaces where you could do all your notes. That'd be really cool. But unfortunately, that's not possible. So this is how you would draw things in 3 dimensions on a two-dimensional piece of paper. Now, the magnitude or modulus or length of a vector, AB, is just its length, and we write it with absolute value bars around the vector. So if vector AB is the column vector 6, 8, that would mean you go 6 in the x direction, 8 in the y direction. How long is this side? This is a famous one. You should be able to do this in your head. It is 10. It's just the 3, 4, 5 triangle doubled. Can you see that? Because you know 3 squared plus 4 squared equals 5 squared. If you double it, 6 squared plus 8 squared, 36 and 64 makes 100. So the length of AB is 10. Any ideas how to find the length of this one? In 3 dimensions, how long is that blue line?
5.
In 2 dimensions, you could do a squared plus b squared equals c squared to get this, right? To get that one? Because that's just 9 this way, 3 that way. That's in 2 dimensions, a right triangle. A squared plus b squared equals c squared. So I would know that that black line, I'm going to write out a squared plus b squared equals c squared. So if I call this black line c, would you agree that that would be 3 squared plus 9 squared? I could write -9 in brackets, but I'm just going to write 9 squared. That's how long c is. Now something very cool happens when figuring out the blue one. Do you see that we made a new right-angled triangle with c? And now if I want to find the blue one, which I am going to call, what letter should we use? H? Let's call this H. Do you see that H squared would equal C squared plus the orange, which is 4 squared? What's C squared? Well, that's just H squared is now 3 squared plus 9 squared plus 4 squared. And if I wanted to find H by itself, it's like an extended Pythagorean theorem. Notice that you just have the first one squared, the second one squared, and the third one squared, all in a square root. You're just using Pythagorean twice, but it works out to a really nice formula. So the length of AB is just a squared plus b squared, that's just Pythagorean. And in 3 dimensions, it's the same idea, just all 3 of them in there. That's really, I don't know. Sometimes when things work out that simple, you're like, no, it must be wrong. We're dealing with complicated math. This should be something much harder. But it is that easy. So if we wanted to actually find the length of that one that we drew, oh, this is an IB formula. You don't get the IB formula booklet. You have to have them memorized. Hmm? Have you had a formula in any of calculus?
But we're not in calculus anymore. This is our advanced math credit.
And you have no formula sheet.
Yes, Mr. G. Take that.
I had a student who graduated from the IB math come back to visit this year.
Instead of wish it in US formulas.
She did. She said the biggest thing that she wishes from high school was that she didn't have formulas, because then university she had to memorize them all.
Who was it?
I bet she was lying too.
Was it Amy? Oh, was it?
Amy? Was it really?
Was it Amy?
No, someone got it. Okay. So let's find the magnitude of this. We just use the formula. The length of V will be all of them squared. Easy to simplify. It is the square root of 106. So I would like you to find the lengths of the following three on your own. First one is just 5. 3, 4, 5 triangle. Second one, root 75, which you could reduce to 5 root 3. And the last one is super exciting, because it works out to a nice number in like it's like a 3, 4, 5 specialty thing in 3 dimensions. Works out perfectly just to 7. Oh wait, try this one on your own.
Oh, crap.
Izzy, look, get him!
Wait, what's your mind?
Oh, you're solving for A?
We're solving.
Oh,
you didn't do it.
what else would you? I put it as a 1 coefficient. I swear. I'm not a very good dad. Oh my god, that makes so much more sense.
And it can be plus or minus, because
Like the same as the other question.
it would work either way when you square root something.
Okay. Stop. Well, that's why.
So we've learned that the vectors I and j are unit vectors along the axis,
No, Eric was a little messed up here.
but you can have a unit vector in any direction, and we use the notation with little hat, that u as little hat is the unit vector in the same direction as u. So we have the unit vector in the direction of 6i plus 3j plus k, and of course, these are bolded, but when you write them, you would have to put arrows over the top. And we're going to write our answer in 3 different ways. So we already figured out this was that nice unit where the length of it was 7. We did that earlier. We figured out that the length of u was equal to 7. So if you want something in the same direction as this, but this has a length of 7 and we want a length of 1, we would have to divide that length by 7. Question.
Why is there one just in black?
Step 1.
Oh.
Step 2. Step 3. So once we figure out that the length is 7, well, then you could write the unit vector as just your regular vector, this is my favorite, and put a 1/7 out in front. Now the length of this would be 1. You could also, just like in matrices, you multiply by a scalar, multiplies each thing. You could also put the 1/7 inside. And it asks for 3 different ways. So a third way is either a point or with the unit vectors. I'm going to circle.
I know, right?
My favorite way of writing unit vector is this one.
Ew.
But the formula for the unit vector is just 1 over the length of the vector times by the vector. So you can do the next two to see if you can get the unit vectors for each of those.
We'll probably be watching.
Hey, how did you do? Did you find out that this one has a length of 29?
I did that.
What?
I did that. I did that.
Do we have to multiply? I wrote 5 squared and I just kept it as a 5. Oh.
Again, I like this, but you could distribute the 1 over root 29.
So we don't have to like simplify it.
You don't have to simplify.
Okay. Okay, what's going on? Oh, yeah.
Okay, you're not allowed to say that. I can say I hope myself.
Yeah.
And the second one,
Wait. Let me look at the calendar.
did you get a length of square root of 61? So the unit vector would look like that.
Wait, it's correct.
Yeah. I don't like this
I don't
form
know anymore.
at all, with the i's, the j's, and the k's.
We have math.
I like the vector form, the column vector with the number out in front, the best.
Okay, no.
Are we
Oh
still
God,
going
I
through
love
with
that. Wait, our first day's on the 5th?
Are we still going through with that
Yes.
though?
So we have exam, a test, and prime day on the
Did we just get Mara again? Captain Mara.
You're in all of it too.
I am.
Yeah. We're all in
the
same.
I wouldn't say Molly.
I am.
Mark could come.
Yes,
You're in
it's not
Catholic. It's not worth it.
You just don't know it yet.
All right, and
I don't know, I just like wouldn't trust myself. Well, I wouldn't just, I know.
if you can find the unit vector,
Wouldn't want them to get hurt.
you can find a vector of any length in any direction. So we have the direction 5, -3, 2. I can find the unit vector of that by first, here we go, finding its length, which is square root of 38, and then I could write the unit vector for you. That has a length of 1. Now, if you want any length, you just have to multiply this one. Right, you can distribute it if you want. I would keep it out front. I actually like, or I would like this. All we're doing is multiplying by that root 7. Yeah. And this is some nice applications. Because if you're trying to program a robot to go in certain directions, now you've got the direction you want it to go in, and then you just tell it how far to go in that direction. And then turn in a different direction, and how far to go in that direction.
Of a verb.
He asked me what the definition of a verb was in literary English.
All right.
That's not okay.
Properties of vectors. Two vectors, right, that go in the same direction with the same length are the same. They don't have to have the same starting point. Vectors are free. They can start anywhere. So we call AB and CD equal, even though they start at different places. Sometimes we fix a vector and call it a position vector, but often we're just talking about, hey, You just need to go in this direction for this far. They're equal vectors. If you go in the same direction, or sorry, if you have the same length, but the direction is opposite, we just make one vector the negative of the other one.
Oh, never mind. I was gonna ask what if G and F would be switched.
Or you could do that as well, right? If you wanted to make them the same, DE equals, DE is equal to FG, but DE is equal to negative FG. Oh, this is not written right. Kind of. Anyways, if they go in opposite directions, the one is the negative of the other one. If you multiply a vector by a scalar, by any number, it's parallel and just becomes longer or shorter. Are these vectors parallel? If they are parallel, there exists some scalar k that you can multiply by this one to get the other one. And this one, it looks like what, 2.5? We could show the math. Oh, it's 2 times. Does it look like 2? Oh, yeah, it does. AB is 4, 5. DE is 8, 10. One is 2 times the other one, so that you know that they're parallel. Same direction, different magnitudes. I guess you could also show that they're parallel by finding the unit vectors of each one, and if their unit vectors are identical, then you would know they're parallel. So there we have C, D, E, and F. And we want, first of all, how are A and B, first of all, if A is 2, 4, and B is 2, negative 1. So basically you're going, but this is my starting point, I'd go 2 to the right and down 1. So then B would be 2, negative 1. Can you see that C, which is negative 6, 3, you're going first in this direction, back negative 6, then going up 3, is just 3. If you factor out a negative 3, it's negative 3 times B. And D is 1, 2, which is exactly half of A. See if you can figure out E and F. E is negative 5 B's, and F was 2 A's. The slope of A is 2, and the slope of B is negative 1/2. What does that remind you of when the slopes are negative reciprocals? They're perpendicular. We're going to learn a new word for perpendicular this unit. Because obviously, perpendicular is used for so many other things in real life that we need a new word. You ready for it? orthogonal. How is that for a good new word? Ortho. Maybe because your feet are at 90 degrees, Jelly. That's why they have the ortho things. Which of the vectors are parallel to 7I plus j? If I write that as a column vector, it has a slope of 1, 7. Can you see that column vector is kind of like a slope vector, but it's like flipped? Instead of rise over run, it's run over rise, because the x is on the top and the y is on the bottom. So if I have a column vector of 7, 1, my slope is 1, 7. If I have a column vector of negative 7, negative 1, can you see that your slope is the same? So it would be parallel. You can also show that something is parallel by finding some number that could go out in front to multiply. And since I can multiply 7, 1 by a negative 1, therefore these must be parallel. But if you found the slope of the next one, it's also 1/7. It's parallel. What about C? What's its slope? Negative 1/7. Not parallel. 35I plus 5j is, I would probably write this as 35 and 5. Its slope is 1/7. And the last one is 1/7 as well. On the next two, I'm going to get you to problem solve, but I'm going to give you the answer. T is negative 32 over 5. And I want you to write the answer for the last one. There's T. There's T. T is negative 25, and S is negative 8/5. You're going to solve these last two on your own. I will have it at the end of the video. Like, I'll put up the answer here without explanation. And I'll put up the answer for the last one without explanation. And you'll have time, if you want to watch the video, to pause it, to look at it after you've tried it on your own.